Have you ever walked down the SDC hallway, turned around, and noticed the fire sprinkler system? Well, we did. Have you ever looked closer at it and noticed that it is full of rust and corrosion? Well, we did. For something that could risk the safety of the students, this design flaw is quite inappropriate. Therefore, we, Team M6, wanted to design a better and more long-lasting solution.
We have chosen the valve to be our part for this project. Based on the type of handle seen and its limited rotation, this is most likely a ball valve. The material in the valve appears to be a copper alloy, judging from the green tinge that the corroded material exhibits, as seen in the photo. This is the natural patina of copper. Based on our research, the material is most likely brass, which is an alloy of copper and zinc. In terms of applied stresses, this part appears to undergo internal pressure, possible leaking, and the force of gravity. Due to these stresses, the material is likely to be heat treated for strength. Furthermore, the fact that this is a valve means that it is most likely a casting, which also supports our prediction of a brass alloy since brass is a relatively good alloy for castings. The valve design chosen for this project has definitely undergone corrosion as seen from the pictures. This is in fact one of its greatest issues. There are many types of corrosion which can occur in this situation. However, given the environmental conditions for this part, as well as the design conditions, the most likely types would have to be galvanic and crevice corrosion. Galvanic corrosion is an obvious issue with this design since there are many dissimilar metals, such as copper, iron, and zinc, in physical contact with each other, allowing for electron transport. These metals are also contained within electrolytes, namely water on the inside of the valve and pipes and moisture from the air on the outside, both of which are capable of carrying and transferring ions. Furthermore, when considering that for a sprinkler system the water may not be treated as well as drinking water, the sprinkler water will most likely contain higher salt, mineral, and other ion concentrations. This can further enhance corrosion through enhancing the differences in potential between the metals. This will most likely occur through the accumulation of mineral deposits such as calcium, since the water in the valve is not actually flowing, as well as the potential changing properties of high salinity environments and the increased concentration of aggressive elements such as chlorine. Moving on, when looking at the physical design of the valve, crevice corrosion appears to be a serious concern as well. The above-mentioned corrosion methods can become further enhanced through crevice corrosion due to the many crevices located in and around the ball valve edges, as well as within the threads. These crevices can cause additional mineral and ion buildup and further enhance the corrosion gradient. Given the current design and its material flaws, we, a team of engineers, set off to design a better solution through the Material Performance Index. Now, let's take a look at what the Material Performance Index is and how it can be used to derive a better material.
MPI is simply referring to Material Performance Index. This is a useful tool to help engineers to select the material based on constraints and requirements for the objective. Plus, in the end, specific limits will be applied to narrow down the choices even further. Now, we will introduce how the material was finalized in our case by calculating and comparing different MPIs.
Well, how did we start? In order to start an MPI derivation, we must consider the four basic parameters, which include function, constraints, objective, and free variables. In our case, the function is for the valve to maintain pressure through a waterproof seal on the fire sprinkler system, as well as to provide a supply and drain point. The constraints in our case include cost of material, which will be $3, hydrostatic shock, which will be 300 psi, strain, which will be limited to 2%, the mass, which cannot exceed 0.5 kilograms, and a safety factor of 2 for all stresses. Our objective includes minimizing cost. Finally, our free variable is thickness.
Before starting the MPI derivation, I will list a few assumptions that we have used throughout our calculations. The first assumption being that the valve is used for water, oil, and gas, which is based off of the WOG designation on our valve. The valve inner diameter will be 1 inch. The valve geometry will be idealized as a pipe with these following variables, which will be used in the calculations. The thickness will be considered 1/10 or less of the diameter, which means we can use simplified thin-walled equations for cross-sectional area and pressure. And we assume the hydrostatic shock will not exceed 300 psi. So we start with the first derivation, which is the hoop stress equation. The valve hoop or circumference differential direction must be able to endure 300 psi of pressure with a factor of safety of 2, which means 600 psi. We start by deriving the cost equation, which is simply volume multiplied by price per unit volume, and then we use the loop stress equation, which is fluid pressure multiplied by R divided by the thickness of the pipe. We change that into free variable form, and then we get the cross-sectional pipe area, which is 2 pi RT for thin-walled pipes, and we put all these equations to get an objective function and an MPI, which is hoop stress divided by price per unit volume, and we get a log-log equation for that, and we plot it, and we manage to eliminate a few hundred materials. Our next MPI is strain, and this is to prevent leakage and avoid thread shearing. So we plotted the Young's modulus versus the price per unit volume and eliminated unnecessary materials that have very low Young's moduli. So we managed to eliminate a few hundred materials. Our third MPI is mass, and this is to minimize transportation cost, make it easier to fit into place, and produce less stress on other plumbing members. We set the maximum mass as 0.5 kilograms. We plotted density versus price per unit volume. We managed to eliminate 1,000 materials which were too heavy for our purposes. We choose to impose a few limitations to eliminate unsuitable materials, including any material that's very susceptible to corrosion in water, any material with very high lead content, any material that cannot operate between negative 20 degrees Celsius to 120 degrees Celsius, and the melting point was set to 120 degrees Celsius to avoid melting during operation. We removed glasses and ceramics to avoid brittle fracture. We want the valve to leak before exploding. We remove flammable materials and rare materials to minimize manufacturing costs, and we also remove any non-castable materials because castable steels are much easier to manufacture. So we ended up picking a CA-15 cast steel tempered at 315 degrees Celsius. So this steel is a stainless steel alloy with a strong corrosion resistant, and is very hard, which is very good for our purposes. It starts out as a cast steel, and it is heated up to austenitization, which is around 800 degrees Celsius, and then it gets cooled very fast, quenched to get dominantly martensitic steel, and then is tempered at 315 degrees Celsius to make it more machinable and stronger.
Given the devastating effects of corrosion, now let's see how this new material and design can be protected.
First, to prevent galvanic corrosion, we can use coating to remove the path for electrons to transform. Based on the research, the most common method is duplex painting, which is applying both epoxy layers and metal layers to prevent corrosion. However, when all the layers are destroyed, the corrosion will still happen, so as a backup, another method is that we can select the material of valves and the pipes with similar electrode potential around plus minus 0.15 volt. In this case, we remove the requirements of different potential energy, which simply means the two types of ions will not have enough energy to diffuse each other in a short time, so the corrosion will not happen either. The next one, for preventing crevice corrosion, there is not that much we can do on material selection, but the quality of finishing surface will lead to the damage directly. Thus, a smooth, polished surface without any sharp angles or narrow corners will always help. So, based on all the calculations and comparison between the brush using the current design and the other available materials, our final choice is 600 WOG stainless steel bowl valve. First, stainless steel has a better performance of corrosion resistivity because of the passive layer. Second, it perfectly satisfied our non-functional requirement, which is minimizing the cost. Since the price of stainless steel is only around 1.5 to 1.6 Canadian dollar per kilogram, and we also specify the maximum weight is is 0.5 kilogram. This means the total material cost will be around 0.75 to 0.8 Canadian dollar per valve. This is pretty cheap. Also, the Young's modulus for stainless steel is much higher than brass. This will provide extra strength on handling hoop stress. Plus, the low density of stainless steel will reduce the applied load to the whole piping system and save the transportation cost.